All around the world, massive gray boxes are rising from the ground. No windows, no signage, and yet each one of these structures consumes as much electricity in a single day as an entire mid-sized city. These are data centers, and they are quietly reshaping how we think about buildings. Here is a fact that stops most people cold. A single ChatGPT query consumes roughly 10 times the electricity of a standard Google search since the AI boom began. The heat pouring out of data centers has become one of the most critical variables in architectural design. Get the cooling wrong, and the servers die. The building fails. The business collapses. Today's video is the story of architects doing battle against heat itself. Let's put the scale of this challenge into perspective with hard numbers. According to the International Energy Agency, the IEA global data center electricity consumption is projected to more than double by 2026. This is not a regional problem. It is a worldwide infrastructure crisis. In major urban markets across Asia, North America, and Europe, power grids are already approaching saturation. A single hyperscale data center can consume the entire output of a local substation. And here is the design-critical insight. Between 30 and 40% of all the electricity flowing into a data center goes not to the servers themselves, but to the cooling systems that keep those servers alive. That means the decisions architects make at the design stage, the layout, the mechanical systems, the building envelope, directly determine whether a data center is financially viable or a perpetual cost sink. Architects who do not understand cooling are designing data centers to fail. In data center design, one metric functions as the definitive scorecard for efficiency. PUE, power usage effectiveness. The calculation is elegantly simple. Take the total power drawn by the entire facility. Divide it by the power consumed solely by the IT equipment. And the result is your PUE. A score of 1.0 is perfect efficiency. Every watt goes directly to computing. A score of 2.0 means you are spending as much energy on cooling and support infrastructure as you are on running the actual servers. The global industry average currently sits around 1.5 to 1.6, a significant gap from best-in-class performance. Google's latest generation data centers average below 1.1. Microsoft and Meta have posted comparable figures at their most advanced facilities. Translated into operating costs, that gap represents millions of dollars in wasted electricity per year, per facility. For architects, PUE is not a number you report after the building opens. It is determined by decisions made at the drawing board. The routing of HVAC ducts, the orientation of server racks, the depth of the raised floor plenum, the placement of fresh air intake louvers, and even the building's orientation relative to prevailing winds. Every design choice either improves or degrades this number. Now let's get into the practical core. Data center cooling falls into 4 major categories, and each one implies a fundamentally different building to design and engineer. First, air-based cooling. This is the traditional approach, built around the alternating hot aisle and cold aisle rack arrangement, separating zones of cool supply air from hot exhaust. Architecturally, this demands a raised floor plenum system and generous floor-to-ceiling heights. Second, chilled water cooling. Cold water circulates through pipework to absorb heat directly at the rack level. The trade-off is infrastructure footprint. Mechanical rooms and cooling towers can consume a substantial portion of the total building area. Third, free cooling, also called economization. This approach draws on outdoor ambient air to supplement or replace mechanical refrigeration during cooler periods. Efficiency gains are substantial, but design complexity increases sharply in climates with high seasonal variability or increasing frequency of extreme heat events, a growing concern for facilities in almost every global region. Fourth, and currently generating the most industry-wide attention, immersion cooling. Servers are submerged directly in a dielectric, non-conductive liquid. This technology can push PUE down to approximately 1.02. The trade-off is a completely different structural and waterproofing design philosophy, floor slab load calculations, fluid containment systems, and liquid management infrastructure must all be rethought from the ground up. Now let's turn to the tools architects can put to work today. AI-driven design technologies are transforming the data center workflow across 4 key dimensions. First, automated CFD simulation. Computational fluid dynamics, CFD, is the technology that predicts airflow patterns and heat distribution across 3-dimensional space. Traditionally, this required specialist simulation engineers and weeks of computation time. Today, AI-powered platforms can ingest a BIM model and return detailed thermal flow maps within hours, enabling iterative design testing that was previously impossible within standard project schedules. Second, digital twin-based operational prediction. Before a single foundation column is poured, design teams can run thousands of cooling scenarios inside a virtual replica of the building. Design errors are identified before they become construction errors, which is where they become exponentially more expensive to correct. Third, AI-driven HVAC control system design. The landmark reference case here is Google DeepMind's deployment of machine learning to manage cooling at Google's own data center facilities. The verified result was a 40% reduction in cooling energy achieved not by rebuilding the physical plant, but by optimizing how existing systems were controlled. This benchmark has become the target the broader industry now designs toward. Fourth, generative layout optimization. AI tools can automatically generate hundreds of rack arrangement configurations, duct routing paths, and mechanical room placements, then evaluate each option against efficiency and cost targets to surface the optimal design solution. Theory is only valuable when it translates into practice. Here are the concrete strategies architects and engineers can apply to real data center projects right now. Site selection is where efficiency is won or lost before design even begins. Cooler, ambient climates, highland regions, higher latitudes, and coastal locations with consistent prevailing breezes offer significantly longer free cooling windows across the annual cycle. Every additional operating hour of free cooling reduces mechanical plant load and improves overall annual PUE. Sites in dense urban centers face compounding disadvantages: elevated ambient temperatures from the urban heat island effect, constrained footprints, and limited grid access capacity. Building orientation is the next critical lever. Prevailing wind analysis should inform fresh air intake placement and natural ventilation pathways from the earliest schematic phase. Mechanical rooms must be positioned for direct, unobstructed access to the data hall. Any routing inefficiency in the cooling loop is energy permanently lost. On structural design, immersion cooling introduces load demands that standard commercial construction assumptions do not anticipate. Floor slabs must be engineered to carry at least 30% greater load capacity than conventional layouts to accommodate the weight of fluid-filled immersion tanks. Finally, the global regulatory environment is tightening rapidly. Jurisdictions across the European Union, the United States, and the Asia-Pacific region are implementing binding energy efficiency standards for data centers. PUE thresholds, water usage effectiveness benchmarks, and carbon reporting obligations are increasingly linked to planning approvals and operating permits. Design teams that embed compliance from the earliest schematic stages are eliminating regulatory risk, not merely managing it. Data centers are no longer simple server warehouses. They are the beating heart of global AI infrastructure, and over the next decade, they are set to become one of the most active, most specialized, and most consequential sectors in the entire construction industry. The architects and engineers who will lead this market are those who design for cooling efficiency from the very first line of the program. Those who can read a CFD simulation output and connect its findings directly to decisions in the BIM model. Those whose teams embed PUE targets and energy certification requirements as foundational design constraints from day one, not as compliance checkboxes added at the end. The global data center construction pipeline is accelerating. The demand for professionals who understand both buildings and thermal physics, who can navigate structural engineering, fluid mechanics, and AI tooling simultaneously, has never been higher. Mastering heat is the new frontier of architectural expertise. We close today with one question to carry into your next project.